Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. This series is the one-dimensional policy choice model. This is the first installment in the series. So in this installment, I want to talk about Euclidean preferences, and majority voting. And this is going to, these are things that I touched on in the overview I did in the toolkit series. But let me start off just giving the basics of the model. All right, so this is in the rational choice framework where we have a set of alternatives, and we'll use capital X for that. But now we're putting more structure on this, and we're going to assume that the set of alternatives is a subset of the real line, and I'm going to use this set inclusion notation for that. And that means if this is the real line, X, well, it could be the entire line, or it could be just an interval in the line, or in fact, it could just be any finite set of alternatives or points on the line. So, so it's fairly general, but we're putting this one-dimensional structure on the set of alternatives. All right, so in the rational choice framework, we have a decision maker, or in this case, we have a set of decision makers. And we'll assume that there are n, lowercase n, decision makers or voters. Let me just use that term. And of course, we assume every voter has has preferences over alternatives that are represented by a weak order. So these can vary across voters, so I have to use a subscript I here, and this P subscript I will be the strict preference relation of voter I, where I ranges from 1 to n. Okay. Now, you know, as we've seen, you know, things get interesting when we have a set of decision makers and they have different preferences, but they somehow have to make a collective choice. Here, we're thinking about them having to choose some point on this line. And, you know, but again, we have more structure than we did when we were talking about Arrow's theorem and these kinds of aggregation problems. And what I want to do in this installment is just start thinking about, you know, what that structure gives us. Okay. Now, I should start off by giving some motivation, I suppose. The set of alternatives being one-dimensional is it's a mathematical assumption here, but it captures situations where the alternatives have this kind of structure. So in political science, a lot of times we're thinking about policies or politicians as lying on some spectrum from more liberal to more conservative. And if it's only that ideological characteristic that matters, then you can think about that as a one-dimensional kind of problem. Obviously, you might want to think about multidimensional problems, but that'll be for a different series. So you can think about alternatives in a kind of ideological sense, from liberal to conservative. It could actually be more literal, that you're choosing the scale of some project, or you know, it's how much you want to spend on a project, what you want the tax rate to be, you know, So, or it could be, how, a little bit less literal, it could be how restrictive do you want to make environmental regulations? And there, 0 could represent no restrictions, and 1 could represent we can't do anything that harms the environment in any way. And then there's a whole spectrum between there. So, this structure, it's a very strong assumption that we're making here, but it still is interesting and worth exploring. So I want to start off talking about specific kinds of preferences that are kind of common in this one-dimensional model. All right, so we will say that the strict preference relation PI is Euclidean if basically there's an alternative that's best for this voter. We call that the ideal point of the voter. And then when comparing any two alternatives, the voter just prefers whichever one is closer to that ideal point. Okay. So you have a favorite policy or alternative, and you just want things as close to that as possible. So the way we formalize that mathematically is we say PI is Euclidean if there exists an ideal point VI such that for any pair of alternatives, the voter just prefers the alternative that's closer to that ideal point. And so I'll write that as a logical biconditional. X is preferred to Y by this voter if and only if it's closer to the voter's ideal point. And I'll just use this absolute value notation here. For example, this is the distance from X to the ideal point. Okay. All right. So with Euclidean preferences, obviously there's every voter's preferences would have a utility representation. So if you have Euclidean preferences, then you're going to have a utility representation. There's going to be, a host of different utility representations, but one possibility would be quadratic, which is when we look at the distance between X and the ideal point, we square that and multiply it by -1. And this is quadratic utility. Another possibility would be we don't actually square it, so we just look at the distance between X and the ideal point, multiply that by -1, and this doesn't have a universal term, but let's just call it Euclidean utility. Okay. Quadratic utility looks like this, and Euclidean utility would look like this. Okay. So either functional form would represent Euclidean preferences with ideal point VI. All right. Here, as you've noticed, there's a subscript on the ideal point because that could be different for the different voters. And then so if we have a list of strict preference relations, P1 to Pn, one for each voter, we call that a preference profile, and we say that profile is Euclidean. Okay, now we're using the same term, but here it's modifying a whole profile, right? We'll say that's Euclidean if for each individual, the weak order in that list for that individual is Euclidean. All right, and we say ideal points given a Euclidean profile. We'll say the ideal points are distinct if for all voters I and j, if I and j are different voters, then their ideal points are different. Okay. Now, just to start off, let's consider a Euclidean profile where the ideal points are distinct and they're in the same order as the voters' indexes. Okay, so person 1 has the lowest ideal point, person 2 has the next lowest, and so on, up to person n. This is just going to simplify notation initially, but we're going to go beyond that in pretty short order. Now, with that assumption, I want to focus on one voter in particular. Well, let's also, let's assume for now that the number of voters is odd. Okay, so that means that in this list of voters, there is a voter in the middle, and that voter will have the index n plus 1 over 2, right? If n is odd, n plus 1 is even, so it's divisible by 2. This gives us a natural number that's going to identify a particular voter. And we're going to call this voter, n plus 1 over 2, the median voter. Now, I'm going to be more general about this pretty soon. I'm going to give a formal definition of a median voter that's not specific to, that doesn't rely on this ordering of ideal points. For now, though, we'll assume this ordering of ideal points, and we will just call this person in the middle the median voter. Okay, so I want to start off with the result. It's going to be one in a series of results with the same spirit that kind of identifies or describes the kind of critical role that this median voter plays in majority voting. Okay, I'll call it a median voter theorem. In my mind, it's really a family of results, but they're all sort of expressing the centrality of the median voter in this one-dimensional kind of setting. Okay. I guess before I do that, I should just recall how we define majority voting formally. So if we have two alternatives, x and y, we can take a majority vote between them, okay? And we'll say that x beats y in this majority vote if the number of people who raise their hands for x, that is, they strictly prefer x, exceeds the number of people who vote for y, meaning they strictly prefer y. Okay, so I'm going to define this in a formal way as a binary relation. It's this P with a subscript M. This basically means that X beats Y in a majority vote, and we say that that relationship holds if and only if this inequality holds. Okay. And we call that the majority strict preference relation, or sometimes I'll drop the strict part and I'll just call it the majority preference relation. Okay. We've talked about different properties of binary relations. This majority preference relation is asymmetric. It can't be that X beats Y and Y beats X. But we've seen that there's no sort of logical reason why it has to always be transitive or have any nice kind of ranking properties like that. So I'll just say in general it's not transitive or negatively transitive. All right, we saw this example of the Condorcet paradox. This was in the sort of general social choice model, and there I said, well, suppose we have 3 alternatives and 3 individuals, and they rank these alternatives like so. Right. Then if we graph the majority preference relation, A beats B, B beats C, and C beats A, and we call that a majority cycle. And that was a challenging problem for majority rule. All right. Now, but here we're in a model with a certain Euclidean one-dimensional structure, and this Condorcet paradox doesn't really apply. Okay. Now it could, or something like it could apply, but we'll see actually that with this one-dimensional structure, the Condorcet paradox is not a problem. All right, so let's just do that next. So we'll state this as, let's call it the Median Voter Theorem. All right, now we're in a much more structured setting now, so I'm going to start off with a bunch of assumptions. Let's assume that X is one-dimensional, so it's a subset of the real line. And let's assume that there's an odd number of voters. And let's assume that we have a preference profile that's Euclidean. And we're going to assume that ideal points are distinct. And let's just maintain that assumption that the ideal points are ordered in the number of the voters' indices. Okay. So this is all, it's a lot of structure to impose, but it still is, it's interesting still because it captures situations of interest. And in particular, if I assume distinct ideal points, then having them ordered in the same way as the indices is really without loss of generality, because if we had ideal points in a different order, we could just renumber the voters and so as long as the ideal points are distinct, that's really just a notational convention. Okay, so the result is that under these assumptions, the median voter's preference actually coincides with the majority preferences. So the way I'll write that is following. I'll say for any pair of alternatives, x and y, x beats y if and only if this median voter, person n plus 1, prefers x to y. Okay, so if we have person n plus 1 over 2's ideal point here, then this theorem makes it trivial to see what the majority preferences are. Why? If I take any two alternatives, x and y, the one that's preferred is just the one closest to the median voter. If I take an alternative z and I compare z and x, well, here z is closer to the median voter, so it's majority preferred. And then obviously, and so we'll call this a corollary. Under these assumptions, I won't write them all out again. The median voter's ideal point beats every other alternative. Okay, and we called that a Condorcet winner. Right, and that means if I look at any alternative x that's not this guy's ideal point, well then, right, if x is not this guy's ideal point, that means this median voter prefers their ideal point to x, and then by this median voter theorem, that means that the median voter's ideal point beats x in a majority vote. Okay, so you can see that the median here plays a super important role, and it's very tightly connected to the majority preference relation. So let's just do a proof of this. I won't be super formal about it, but let's consider any pair of alternatives, x and y. And what we need to show is that, well, we need to show a biconditional statement, right? That x beats y if and only if the median voter prefers x to y. Now, when I write a biconditional like that, that really is, it's really combining two conditional statements. One of them is that if x beats y, then this median voter prefers x to y. And the other is the reverse conditional, which is if the median voter prefers x to y, then x is majority preferred to y. Okay, so to prove this theorem, we have to prove both of these conditional statements. So I'm going to start off with two, actually. Okay, so we're going to prove this conditional statement. So I'm going to suppose that the median voter prefers x to y, and I'm going to show that x beats y in a majority vote. Okay, so let's think about what it means for geometrically for the median voter to prefer X to Y. Let me draw a real line here. And without loss of generality, I'll put X to the left of Y. Any argument I make can be reversed in case X is bigger than Y. So this is really without loss of generality. Now, what does it mean then in terms of this picture for the median voter to prefer X to Y? It means he's closer to X than to Y. So I'm going to demark the midpoint between X and Y. Okay, it's just the average of the two. So that is exactly the same distance from X as it is to Y. If the median voter prefers X, that means the median voter is somewhere to the left of that midpoint. Okay. Now, wherever that median is, remember that we're assuming the ideal points are ordered in the same order as the indices. Now, let's suppose the median ideal point is, suppose the median prefers X. So there's somewhere over here to the left of that midpoint. Okay, but then by assumption, all these guys to the left of the median, right, with indices that are smaller, are also to the left of that midpoint. Okay, so so the way I'll write that is I'll say since person n plus 1 over 2's ideal point is to the left of that midpoint, then we have the same thing true for every voter going from 1 all the way up to n plus 1 over 2. Okay? All right, but that means that if I were going to put those voters over here, they would all be to the left of that midpoint, which means their ideal points are all closer to X than they are to Y, which means they all prefer X to Y. Right? So that means that all of these guys prefer X to Y. But now that means there's a majority of voters who prefer X to Y, and therefore X will be strictly majority preferred to Y. Put that up here. All right, so what I've done is I said, well, let's suppose that the median preferred X to Y, and I showed, well, then X has to be Y. So I've proven that conditional statement, and that finishes the proof of this second conditional statement. Now we have to now get back to number 1. All right, so now we're going to assume the antecedent of that, which was that X beats Y. Okay, and we need to show that, that the median voter prefers X to Y as well. Okay, all right, let's draw the real line again, and we'll put X here to the left of Y. Again, that's without loss of generality. And here's the midpoint between the two. We need to show that the median voter prefers X to Y, so we need to show that they're to the left of that midpoint. Okay, that means they're closer to X than they are to Y. Well, the way I'll do this is you can think of it as a proof by contradiction or just a proof by elimination of cases. So what are the cases? We can either have case one would be that the median voter, their ideal point is to the left of the midpoint. That's what I want to show. Case two is that the median voter, their ideal point is exactly the midpoint. And the last possibility is that the median voter's ideal point is strictly above the midpoint. Okay. All right, so the one we want is the first one, and I'm going to rule out the last two using our assumption that x beats y. All right, so in the last case here, in that case, let me draw it like this. That means that the median voter is actually to the right of the midpoint. That means that their ideal point is closer to y than to x. But in the second conditional statement that we just proved, we showed that if the median voter prefers one alternative to another, then so does a majority of the voters, okay? So in this case here, then, if the median voter's ideal point is above the midpoint, that means that they prefer y to x. But then, we've shown when the median voter has a preference, then so do a majority of voters. So this would mean that y is majority preferred to x, but that is in conflict with this assumption that x beats y. You can't have x beats y and y beats x. So that's a contradiction that rules this possibility out. Okay. So the second case is that the median voter is right at the midpoint. Okay. Right. So that would mean that this midpoint is the median voter's ideal point, and then everyone from person 1 up to n minus 1 over 2, their ideal points are all below the median voter. Person n plus 3 over 2 all the way up to n, their ideal points are all above the median voter, okay? All right, but that would mean that everyone below the median they all prefer x to y. Everyone above the median, they all prefer y to x, right? Their ideal points are all closer to y. But then that means that the number of people who prefer x, right, is the same as the number of people who prefer y. The number of people who prefer x to y, that's just n minus 1 over 2. And the number of people who prefer y to x, those are the people above the median. Well, there's just n minus 1 over 2 of them as well. So these numbers are equal. What that means is that in this case, x and y would tie. There would be a majority tie between them, and we can't have x beating y. Again, that contradicts our assumption, and so we can rule that case out as well, right? It's a long way of saying, if the median were at the midpoint, there would be just as many people above the median who prefer y as below the median who prefer x. And again, that is inconsistent with the assumption that x beats y. So that leaves just this case here. Right? So we've shown that if x beats y, then the median voter has to be to the left of that midpoint. And that implies that the median voter prefers x to y, that their ideal point is closer to x than it is to y. All right, so we've shown that if x is majority preferred to y, then the median prefers x to y. And that gives us both directions of the biconditional statement. So that means that the majority preferences are the same as the median voter's preference. So I won't say much more about this. I will point out that there is a strategy that we used in this proof that can be helpful. We proved the second conditional first, right? Let's go back. We proved the second conditional first because, once we had that, it actually helped us rule out a case when we were proving the first conditional statement. That's something that you can do in a proof. If you prove something, then, if part of the proof consists of proving a certain step or a claim, well, if you've actually proven it, it's true, you can use it later on in the proof. So, there's maybe no such thing as the perfect proof, but some proofs are better than others. And if you can find a way of being more efficient, of, killing two birds with one stone, so to speak, then that can be good. It can save time and it can make the proof shorter. So that's enough on Euclidean preferences and majority voting for now. In the next installment, I'll return to that briefly, and I want to connect that back to Arrow's theorem, because we've basically shown that with this one-dimensional structure, Arrow no longer holds, right? I mean, Arrow's theorem is correct, but in Arrow's theorem, we assumed that individuals could have any weak orders. And here we're ruling out lots of weak orders because we're assuming Euclidean preferences. All right, so I'll return to that. I'll connect the discussion to Arrow, and then I want to talk about a more general approach to the one-dimensional model. Euclidean preferences are easy to work with, but it is a very strong assumption, and we can actually do away with a lot of that and prove some of the results in more generality. So that's what's coming up in the next installment. I hope to see you there.